Alright, you can scan the QR code while waiting others to join. Yeah, before we go further, for today we're going to enter new chapter. Yeah, but this chapter will not coming up for your exam. Okay, so for today we're going to enter chapter 4, which is bipolar junction transistor, which is also known as BJT. Yeah. Okay. All right. Before that, have all of you read the SOP for your test that will be in this week? Any question regarding the SOP for the test? I hope you read the SOP earlier. Okay, and if there is any questions that you want to ask or anything that you want to confirm with me, you can confirm. Okay, so make sure that you you prepare all the things that need to be with you before the test. Yeah, which is you are allowed to use calculator. Very good. Yeah, you are allowed to use calculator. In my university time, I didn't allowed to use calculator at all. So very good, and you are allowed to use calculator. Okay, make sure that you have a blank paper. You need to write your answer, right? And you have your software, yeah, PDF conversion software, PDF file conversion software. And when you write your answer, please make sure that I can read your answer. Okay, and when you take the pictures too, please properly take the pictures. It is not blur anywhere. Okay, so your answer can be clearly seen. Okay, and your handwriting too. And be careful with the time for each test. I share with you this one. Wait, yeah. Be careful too the time for each test, yeah, for each paper. Okay. Okay, for those who just joined, now I'm just go through a little bit about the SOP for the test. Yeah, so be careful about the time. Okay, the duration of the time. Yeah, for paper 1. Okay, the it's only allowed 20 minutes for you to answer the questions. Yeah, and then for paper 2 also 20 minutes. Yeah, and after that you have to submit. Okay, you have to submit your answer, and then after that there will be paper 3. Okay, so paper 3 you are allowed to download at this specific time. Okay, so each paper there are specific time for you to download. Yeah, okay, so be careful with this time. Okay, with this time duration. So if let's say you miss one of those paper, please quickly contact me. Okay, let me know. So I will notice here. All right. Okay, so I hope no more questions, yeah, regarding this. I hope you are familiar with this test. Okay, so let's proceed to this topic. And let's send a window. Yeah. Yeah, all right. So for today's topic, okay, we're going to enter chapter 4, which is bipolar junction transistor, BJT. Okay, which is we will focus on DC analysis. But today we will not enter DC analysis yet. Okay, we just introduction about bipolar junction transistor, or also known as BJT. Okay, so when we said about transistor, we have lots of transistors. Yeah, we have FET, we have MOSFET, we have BJT. So for today, first of all, we will learn about introduction about bipolar junction transistor, or also known as BJT. Yeah. So these are the learning objectives. Someone just join. Okay, so these are the learning objectives for today's class. Yeah? Okay. Okay, so you should, for today's class, you should able to describe the basic structure of BJT, and then explain and analyze the basic BJT bias and operation. Okay, and also discuss the function of BJT as an amplifier and parameters and characteristics. Okay, so today we're going to focus on these three things lah. And application might be tomorrow, right? Okay, so this is attendance for those who haven't looked your attendance yet. Okay. I hope all of you have recorded your attendance. Yeah, I will proceed. Okay, so a little bit revisions. Okay, so a revision about Zener diode. Okay, so Zener diode will come out in your test. Yeah? So Zener diode, so the symbol is like this. Okay, if normal diode, the symbol is all like this. But for Zener diode, there's a letter like a Z. Okay, behind here. Okay, so it refers to Zener diode. So Zener diode is different with normal diode, since that it's manufactured to be worked in breakdown region, right? So if regular diode, it will work in forward region, but Zener diode is specifically will work in breakdown region. Okay, so this is very important for you to know. Yeah, ZK, so it means that Zener ni, so this is the minimum. ZM is the minimum voltage value currents of the currents for Zener to work. Okay, but and it cannot be exceed ZK, Zener ni. Okay, and then so there are three types of Zener. Okay, for your diode analysis: fixed VS and RL, fixed VS and variable RL, variable VS and fixed RL. For your test, only this will come out. Yeah, fixed VS and fixed RL. Okay, fixed VS and fixed loop. Okay, for this will not come up for your test. Okay, we're going to focus only for this part. So please, for your revision, only focus for this part. So for Zener, for you to determine if the Zener work or not. Okay, so here is the important formula for you to remember. No, formula will be given in your test. It's very kind of teachers. Yeah? They'll give you formula too, so you don't have to remember. Okay, so but you need to know that this is to know either the Zener is on or the Zener is off. Yeah, if it is more than V is more than VZ, so it means that the Zener is on. If the value of V is less than VZ, so it means that the Zener is off. Okay. Okay. So with that, for your revision, okay, so today we're going to go for transistor. So what is transistor actually? So transistor is a solid state device that used for amplifying, controlling, and generating electrical signal. So that is the function of transistor device. So there are lots of transistors out there. So these are the example image of transistor that can be found in any circuit, yeah, any board circuit. Okay, it is widely used in electronic equipment such as computers, calculators, radios, communication satellites, and also in your motherboard, yeah, computer motherboard. If you open your computer motherboard, you can find like this, and there's a lot of transistors as well inside that. Okay, so these are the just a little bit background of transistors, yeah. So what is transistor actually? So transistor, there are two types of transistor, yeah. Yeah, we have bipolar junction transistor, known as BJT, and we also have field effect transistor, which is FET. Okay, this we're gonna learn later. Okay, first of all, we're gonna learn about bipolar junction transistor. Okay, the word bipolar. I think bipolar also famous with bipolar mental illness, yeah, bipolar characters, right? So sama with transistor. Why we call it bipolar? Because it has two types, both types of uh, what transist of diodes, yeah, and both the minority and the majority carriers for the for the currents, yeah, will involve in the operation of the transistor. Okay, we're gonna look later on why it is called as a bipolar. Okay, so transistor is like two diodes connected. Okay, so this is two diodes, it is connected. Okay, so p type, it has two types, yeah, PNP and also NPN. Okay, so if it is PNP, it means that combination of P type, N type, and P type. Okay, so the diodes configuration will look like this, yeah. If you want to make a symbol of through diode, they're gonna look like this, the configuration of diode, yeah. P, and then connect here and here. Cathode here will meet the cathode for another diode, okay, which will make N here, and then here is P type again, and cathode, anode, sorry. So for NPN in the middle, it will be P type dop, yeah. So each region have different doping concentration, yeah. Each region have different doping of concentration, and it is widely used as switch and amplifier. Okay, so transistor widely used as switch because you will the current able to be controlled, yeah, able to be controlled. Okay, if it is like this, the base, the collector, the emitter, you can control the currents here. So that's why it is known as switch, and also amplify because it will amplify the currents. Yeah, currents here can be amplified by adding these two currents. Yeah, so it's also can be used as amplifier. Okay, I think you can understand this more when we look into the characteristic or how the transistor work. So next, so what is a bipolar junction transistor? So bipolar junction transistor, or also known as BJT, is constructed with three doped semiconductor regions, yeah, separated by two PN junctions. Yeah. It's combination of two PN junctions, yeah, and it has three doped of semiconductor regions. And then the three regions known as emitter. Okay, we have emitter. So the function of emitter is to send the carriers, yeah, send the carriers into the base region and then into the collector. Okay, and then what is the function of base? We also have base here. So base is a act as control region. Okay, base is controlling. It is act as control region where the carriers flow depending on the bias voltage that we apply at the base part. Yeah? And then collector, as the name given, it collects. Yeah? It collects the carriers. So we have three regions in BJT that you have to know. Yeah? E, B, and C. E for emitter, B for base, and C for collector. And then there are two types of BJT, as I mentioned earlier. We have NPN, which is two N regions separated by P region in the middle. Okay, and we have PNP, which is two P regions separated by N region in the middle. Okay, and the bipolar refers to why it is called as bipolar, because both majority and minority carriers take part in the current flow. So it's different with diode. Yeah? If diode, only the majority parts will take part in the current flow. Okay, depending on what majority carriers inside the diode. But for bipolar, both will take part. Yeah? The majority part and the minority part both will take part in the flow of currents. Yeah. So N types. So this is this is a revision for diode. Yeah, usually N-type we have electrons as majority carrier, right? So for and p-types we have holes as majority carrier. So since that BJT is combination of N, P, both type of this, so during NPN, yeah, during this combination, electrons and holes both will take part during the when the currents flow. Same with PNP. Okay, PNP, the majority will be holes, right? But the minority, which is the electrons, also will taking part uh, in the currents flow, right? So this is the basic epithelial planar structure of BJT. Okay, so this is the emitter. It's located here, yeah, base and the collector here. Okay, I think this is just only for you to know now. Okay, the structure inside BJT. Okay, so this is the structure and symbol for BJT. Okay, so for P and P type, yeah, for P and P type, so it is separated with the N in the middle, N region in the middle. So the base will be N. Okay, the emitter and the collector of this type of BJT will be P region. Okay, so it also can be represented like this, yeah? P and P, where this is the collector, this is the base, and this is the emitter. Okay, and in circuit, it will be symbolized as like this. Okay, this is the symbol of BJT when it is presented in the circuit diagram. Okay, so C refer to the collector, B refer to the base, and E refer to the emitter. And you can look here, yeah, the arrow here represent the currents flow, the flow of currents inside this transistor. Okay, so here the currents for PNP, yeah, the currents flow from the emitter. So it means that the currents from the emitter will flow to base and then will go to the collector. Okay. Alright, so next look into the NPN type. Okay, so NPN type, the P, okay, the P region will divide, okay, will be in the middle, okay, will separate the N region, yeah. So the N region will be the emitter and collector, okay, and P will be the base, okay. Alright, so what I want to highlight here is the current flow. It is different between PNP and NPN. Okay, be careful. For NPN, the currents flow to the emitter, but for PNP, the current flow from the emitter. Okay, the current flow from the emitter. So be careful with the direction of the currents. So based from the direction of the currents here also, you can tell the types of the transistor. What type is it? If the currents flow to the base, okay, to the base, towards the base, so it is a PNP type of transistor. But if the currents flow out from the base to the emitter, okay, to the emitter, it is NPN type of transistor. Okay, so the equation of the currents is same for both, yeah, PNP type and NPN type. Okay, so IE for NPN type is equals to IC, which is current flow from the collector, plus current flow from base, will give you current flow from the at the emitter. So same for PNP, current flow from the current flow from emitter will be divided into base and collector. So the total of current from base and collector will give you total current flow from the emitter. Okay. Yeah, up until here it's very basic of transistor, yeah. So next, Okay, so to helps you to understand well this C, D, and E. Okay, so just imagine that the currents, the BJT is just like your pipe, yeah, your pipe. Yeah? So the one that you can spin the pipe, yeah, is what we call the base. Okay, so because the base, the one that control the current flow. Okay, emitter is at the emitter at the beginning of the base, and the collector is at the end. Yeah, so force, voltage, or currents, yeah, flow. Okay, and then water flow is just like the currents and the amplifications. Yeah, base will control. If base allow that a lot of currents to flow, it will amplify. Yeah, at the collector will amplify the currents. It means that the collector will receive lots of currents. Yeah. Okay, next. Okay, let's look the operation, how BJT works. Okay, how BJT works. Okay, yeah. All right. So for this operation, okay, let's look one types of BJT, which is NPN structure. Okay, NPN structure. So it will be goes same as PNP as well. All right. So NPN structure. So this is the collector. This is the base. Yeah, the base will gonna be in the middle, and this is the emitter. Okay, the end part, end region, it is a very at the collector. Yeah, end region at the collector. It is a very lightly doped. Okay, it is lightly doped, and it collects the current carriers. Okay, so that is the characteristic of the end region at the collector. For the P region at the base, okay, it is a very lightly doped as well, and it helps to control the flow of currents. Yeah. So, and then for the end region at the emitter, okay, it's quite different compared to the collector. It is a heavily doped region. Okay, so at the emitter, it is a very heavily doped region. Okay, and it emits the current carriers. Okay, it will emit the current carriers. So the emitter is rich in current carriers. Okay, lots of currents will flow in emitters. Yeah, it's rich in current carriers. It sends the carriers into the base region. Okay, into the base region and onto the collector. So from the emitter, it will send the current into the base region and to the collector. So the collector will collect the carriers, and the emitter emits the carriers. Yeah. So the base acts as control region, and it can allow none, some, or many carriers to flow from emitter to collector. So let's look into a diagram of this. Okay, let's look into detail based on this diagram. So the N-type emitter region has a very high density of conduction bands. Yeah, so it means that it has lots of free electrons. N-type emitter regions for this. Yeah, for these emitter regions, they have lots of free electrons, and since that at the emitter, okay, they have lots of free electrons. These electrons is easily diffused through the forward base BE junction. Okay, BE junction is here. Okay, base and emitter junction. Yeah, so it means that since the emitter have lots of electrons, free electrons, these free electrons can be easily diffused, okay, to these two junctions. Yeah, and since that the base have a p-type base region, okay, p-type base region, and since p, yeah, they have hole and it is a lightly doped, it shows that, so it means that since it is lightly doped, yeah, so it means that this depletion region of this p-type is very narrow. Okay, it's it is very small. Sorry, it's not narrow. It's very small here. Okay, it's because the depletion region is very narrow. Becomes okay. It becomes narrow. Okay. So since some of the free electrons flow here, okay, flow here, so they will combine. Okay, this will make a recombination, holes and electrons. Okay, there will be a recombination of holes and electrons. So there will be a small percentage of numbers of free electrons inject into the base region, okay, inject into the base region and combine with these holes, yeah, with these holes and move as valence electron through the base regions. Yeah? So these are the valence electrons that combines with the holes inside the p region here and move as a valence electrons. What will happen since that this depletion is very narrow, right? So most since that the emitter also contains a lot of free electrons. So other electrons that from the emitter will flow to the collector part. Yeah, others will flow to the collector part. Only some of the electrons will go into the base part. Yeah, base area. Yeah, because of the depletion region too small here. Yeah, so the less number of free electrons goes to the base here will then combine, yeah, recombine with the holes that exist in the p-type region here and will produce a valence electrons, yeah, valence electrons, and will move, okay, and the electrons will move towards here again, yeah, and will come again to the emitter part here. Okay, so here, right? So since that the you can see here that a little blue arrow here, it represents the whole currents. Okay, as we learned before in diode, yeah, PN diode, there is a whole current axis. Yeah, so the amount of the whole current is very small. So that's why it's very little current will flow back here, which represent a whole current, yeah, a whole current. But this current can be neglected because the value is very small. Yeah. So when the electrons recombine with holes as valence electron, leave the crystalline structure, yeah, leave the crystalline structure of the base, and they become free electrons in the metallic base lead and produce the external base current. Okay, so here, yeah, it will produce as external base current. Next, what will happen at the collector part then? Okay, at the collector part, okay, as the free electrons, most of them will move toward the BC. Here is the BC part, yeah, base collector part. So since that lots of free electrons move towards the BC junction, okay, they are swept across into the collector region by the attraction of the positive collector. So this, yeah, this is negative, right? And the external source here is represent like this. So positive region meet negative region here, so it will be a reverse bias, right? So reverse bias, so since it is a reverse bias, though most of the electrons here will sweep across the collector region, okay, because most of them will attract to this positive region of the external source of the battery. Okay, so the free electrons move through the collector region, okay, move through the collector region into the external circuit, okay, into the external circuit, and then return into the emitter region again. Okay, so the free electrons here will move into the external circuit and then again will enter the emitter region. Okay, so you can see that lots of currents come to the emitter regions, okay, the external part from the collector and also the free electrons, okay, valence electrons that come out from the base also will go again into the emitter. So that's why the currents at the emitter will be large. Okay. All right. Okay, so that will cause the current at the emitter. Okay, the current at the emitter is slightly greater than the collector currents. Yeah, because the small current from the base and also the lots of current from the collector here. Okay, so this is how the currents, the BJT operates, right? Okay, so let's look next. So that's why IE, okay, IE is equal to IC plus IB. So these are the reasons why. Alright, so let's look to the next one, which is the BJT characteristics and parameters. So for BJT characteristics, yeah, it is familiar, okay, with DC beta and alpha DC. Okay, you have two. We're gonna have two characteristic, which is beta DC or DC beta and also alpha DC. So what is the difference between beta DC and alpha DC? So beta DC or DC beta is the ratio of the DC collector current, okay, current that come out from the collector, okay, DC collector current to the DC base current, okay, ratio from the collector to the base currents. Yeah. So the value of beta DC range less than 20 to 200 or higher, usually around this value. Yeah. However, and yeah, this is IC over IB, okay, current from the collector divided by the current from the base. Yeah. And then for alpha DC, okay, alpha DC is a ratio of the DC collector current, okay, to the DC emitter currents. Yeah, so this is DC collector and also emitter. Okay, so the value of this alpha DC, yeah, usually range from 0.95 to 0.99, and it is always less than 1. It will not be 1. Okay, it is always less than 1. Why? What is the reason? The reason, okay, for example, like this, yeah, emitter currents, yeah, emitter currents usually around milliamps, yeah, and beta currents, base currents also usually around milliamps, and this is the biggest, yeah, the biggest, usually around micro ampere like that, and then collector currents also around milliamps. So if you see like this, yeah, since that the what the formula is IC, which is current from the collector divide with the current from the emitter, so it will gives you IC 99 milliampere divide with 100 milliampere, it will give you around 0.99. So this is the maximum value of currents for emitter, base, and collector. So it will not be more than 0.99. Okay, so this value usually around this range, yeah, 0.95 to 0.99, depending on how much doping and how that the base is controlling the currents inside the BJT. All right. And since that these two, yeah, these two also can be combined where beta is equals to alpha over 1 minus alpha. Okay, so you can also get the value for beta. Okay. Let's say that the currents for base is not given. You only have these two value. So you still can find the value for beta by using this formula. Okay. Okay, so what is the function of beta DC and alpha DC? So beta DC and alpha DC is used to analyze, yeah, analyze the BJT circuit. Okay, so for you to analyze the BJT, the performance of the BJT, then you have to calculate the beta and alpha. So it is used to uh, for you to measure the BJT characteristics, yeah, circuits. Okay, for example one, let's do it for example one. Determine the DC current gain BDC and the emitter current IE for a transistor where IB, okay, IB is equals to 50 microampere and IC is 3.65 milliampere. So how to solve this? Since that we know, yeah, beta DC is equals to IC over IB. So 3.65 milliampere divided by 50 microampere, you will get 73 without any units, yeah, without any units. And then 73. So this is the value for beta DC. So how to find IE? IE, since that this is the formula for the currents, yeah. IE is equals to IC plus IB, so you will get the total currents for IE is 3.70 milliampere. Okay, and in your test too, just now I forgot to say, don't forget about the units and please don't write wrong units. Yeah, be careful about the milli, micro, and all those things. Yeah. All right, so BJT circuit analysis. Okay, when I say IB here, so IB it refer to the DC base current, currents that flow to the base, yeah, to the base from the BBB, okay, from the external source here. Usually it's given. Okay, so IE, what is IE? IE is the emitter current, currents that flow from the emitter currents, and IC is current that flow to the collector, to or from the collector. Okay, so VBE, okay, VBE is the voltage at base and emitter. So at these two we call as VBE, right? Base and emitter. Okay, VCB, CB here. Okay, so VCB here is a voltage at collector with respect to the base. Okay, it is voltage at collector with respect to the base. Okay, VBE is a voltage at base respect to the emitter. Okay, and VCE, E and E, VCE here is a voltage at collector with respect to the emitter. So please get used with this, yeah, VBE, VCB, VCE. Okay, and IB, IE, IC. I think IB, IE, IC is okay, but VBE, VCB, VCE might be confused. Yeah, might be confusing, so be careful. Yeah, and VCC is the external voltage here, and VBB is external voltage at the base. VCC external voltage at the collector. Okay. All right. So let's look at this. Yeah. So for example, so this in this circuit, okay, in this circuit, they are using PNP or NPN. They are using PNP or NPN. Which one?
NPN.
NPN, right? So they are using NPN. Okay. Right. So they are using NPN. So since that they are using NPN and the voltage here, yeah. Okay. So the voltage here is positive and connected with positive, so it means that same polarity, so it is a forward bias. Yeah, here is a forward bias, and this is positive. Sorry, this is NPN, right? NPN. So this is negative actually, yeah, negative, and then connected with positive. So it means that different polarity, so it is reverse bias. So here it is reverse bias and here it is a forward bias. Okay, and also take note that the base emitter, yeah, at the base emitter, there are a very few voltage drop here, since that this is a forward bias, right? So forward bias, there are a few of voltage drop. Okay, put voltage drop around 0.7. Okay, sometimes this value can be neglected, but in this time, yeah, we will take note, yeah, this value. And also sometimes this value can be very bigger, can be very big here, so it depends. So in this case, the VBE here, okay, the voltage drop here is around 0.7 volts. Okay, so the voltage across resistor, okay, so to find the voltage across resistor RB, so it means that VRB, V at this point, yeah, VRB. Okay, be careful with the sentence too. Okay, in your test also, when they say voltage across any resistor, it means that voltage at the resistor, across the resistor. Yeah. So voltage across resistor RB. Okay, so voltage at this point, VRB, is equals to VBB minus with the potential difference at this. Yeah, VBE. Okay, so VBE is 0.7, VBB is not, yeah, the value is VBB, so VBB minus VBE. So you will get the voltage for VRB, voltage at the resistor RB here. Okay, next, current. So current across the resistor IB. Okay, so since that you it's given the value of RB, okay, so to find the current across the resistor RB, across this, yeah, IB current, it is IB equals to V equals to IR, right? So to find I is B divided by R. So VBB minus with the potential drops, yeah, VBE divide with the value of resistor. Okay, so you will get the value for IB. Next, voltage at the collector. Okay, voltage at the collector with respect, which is VCB, with respect to the emitter. So it means that VCE. Okay, voltage at the collector with respect to the grounded emitter. Okay, so it means that VCE. So how to find VCE is VCC minus with VRC, voltage at the resistor here. Okay, so VCC minus with VRC, then you will get VCE, right? So to find VRC, you need to find the value of IC first, the current that flow here. Okay, so voltage across RC is VRC equals to IC times RC. So this is Ohm's law, right? So voltage at the collector with respect to grounded emitter is, yeah, VCC minus with this value. Okay, so just this value put inside here. Yeah, VCC minus IC times with RC. Okay, you will get VCE. Next, where IC, okay, IC is BDC times IB. So this come from the beta just now, yeah, beta DC formula just now, which is IC over IB. Okay, so IC over IB, since that you know IB just now here, right? You have calculated IB just now. So beta DC might be given in the equations. Yeah? So voltage across reverse bias collector base junction. Okay, reverse bias collector base junction, which is VCB. Okay, voltage across reverse bias collector, and then the base junction. Yeah, the base junction. So here, so VCB is equals to VCE, yeah, VCE minus VBE. Then you will get VCB. Okay, so this is all the formula in case, yeah, in circuit analysis. Okay, they will ask, if they ask you how to find IB, then you know how to find IB. How to find VCE, so this is the formula how to find VCE, and then how to find IC also. Okay, these are the formula that you need to familiar with. Okay, you need to know. Okay. Okay, so let's look at the example here. So determine IB, currents that flow IB here. So this is IB. IC, okay, here is IC. IE, here is IE. And then VBE, VBE, here is VBE. VCE, here is VCE. And then VCB, here is VCB in the circuit below. And then it's given to you the beta DC value is 150. So so since that we take into account, yeah, VBE is approximately 0.7 volts, yeah. So for you to find IB, I think you can use just now, like just now, yeah. IB is VBB is given, yeah, VBB minus VBE, okay, VBB minus with VBE, which is 0.7, and then divide with RB, then you will get the value of IB. Okay, once you get the IB, you can find directly with the value of current at the collector, IC, using this formula, right? So the value of the current at the collector is 64.5, okay, times 150, the value is given here, with the value of the currents of at the base. And then once you get the IB and IC value, you can always find current at the emitter. Okay, so IC plus IB, you will get current at the emitter. So solve all the currents part. Okay, so how to find the VBE, VCE, and VCB? Okay, so first of all, VCE is equals to VCC minus with ICRC. Right, since that you know the currents flow here, how many currents flow here, you can always find the value of voltage at this resistor. Okay, so 64.5 times 100 ohm, you will get 3.55. So once you get the VCE value, you can always find the VCE. Okay, so VCE is VCB is 3.55 minus with VBE value, which is 2.85. Yeah, 2.85. So you will get the value of all the value, right? VBE, and then VBE with VBE, and then VCE, and also VCB. Okay, so usually VBE is the value of VBE is the potential drops at this point, yeah, for this transistor. If it is usually if it is a forward bias, yeah, forward bias, the value is same as silicon, yeah, which is 0.7 volt, approximately 0.7 volts. Okay, I hope it's clear. Yeah? So since the collector is higher voltage, so the voltage at the collector is higher than the base, the collector base junction is reverse bias. Okay, at the collector here, the voltage is 10 volts, right? While the base here is 5 volts. So the junction at the collector base is reverse bias. Okay, reverse bias. Okay, so next, let's go to the current voltage characteristics. Okay, so I think current voltage characteristic we have learned when we are understanding the diode characteristic. Yeah, it shows the characteristic curves between current and voltage, yeah, also known as IV curves. And if the input characteristics, yeah, the relation between the input current and also the input voltage for different values of output voltage. For the output characteristics, yeah, to know the output characteristic, it is a relation between output current and output voltage for different value of input currents. Okay, so let's look the BJT basic operation. Okay, so BJT basic operation region, okay, to produce a desired mode of operation, okay, BJT usually it is combination of two PN junction, okay, and it must be correctly biased, okay, it cannot be wrongly biased. An NPN transistor, okay, let's say we are using the NPN transistor. Usually, for example, we are always using the NPN transistor, yeah, for illustration. So the operation of the PNP is the same as for NPN, except, yeah, why we are using NPN? Because usually the operation NPN and PNP is same, except that the roles of electrons and holes, yeah, the roles of electrons and holes, what are the major? For example, for PNP, instead of the electrons, holes will be the majority, okay. And then the bias voltage polarities, yeah, the bias voltage polarities might be connected the other way around compared to the NPN. Okay, for just now, for NPN, at this part, yeah, for the base emitter, okay, for the base emitter just now, it is connected as, since that this is NPN, right? So it is connected with positive, right? Positive and positive, right? For NPN type. But for PNP type, the base will be, okay, the base will be connected with the negative part, yeah? So because, sorry, PNP, PNP, because here is in the middle is N, yeah? So negative, okay? So the polarities of the bias voltage might be different, okay? So the current direction are all reversed, okay? The direction of the currents also reversed. So please take note of these three, okay? So a single PN junction, usually they have two types of bias, right? As we have learned before, we have forward bias and we have reverse bias. But for BJT, since that they are combination of two PN junction, so we have four types of bias. Okay, so four types of bias, where we were going to look here now. Okay, so for example, let's look here. Yeah. Okay, so in this current, yeah, so in this circuit, yeah, the external source that connected to the base here is variable. It means that it can be changed, the value of the at the base, yeah, and the value of the currents also can be controlled. Okay, same to VCC. Okay, so assume from here, yeah, assume the VBB. Okay, the VBB here is set to produce a certain value of IB. It means that the range of voltage here is set to a certain voltage, so that the current flow for IB also is set to flow at a certain value of currents. And the value of VCC here is 0 volts. Okay, assume, okay, it is 0 volts. 0 volts. So both the base emitter, okay, base emitter and base collector, both were gonna be in forward bias, yeah, forward bias. Both of them were gonna be forward bias. Okay, so since that it is forward bias, both of them were gonna have potential drop 0.7 volt, 0.7 volts, yeah. Okay, next, the base current flow, yeah, the base current then will flow through the emitter. Okay, the base current, since that here is 0, yeah, so the base current here will flow through the emitter. Okay, will completely flow through the emitter, and only a slightly current will flow to the collector. Because of why? Because of at the collector part there is a resistance. Okay, so there is a resistance, so it means that less current will flow here and more current will flow here, since that there is no resistance at all. Okay, no borders at all, so they will flow more here. Okay, so much current will flow at the emitter part, since that it is the low impedance part, right? So you can see when we are plotting the currents value, yeah, the currents at the collector towards against the voltage of the collector and the emitter. Okay, collector and the emitter at certain point. Okay, at certain point before it reached the 0.7 0.7, which is a knee voltage for the transistor, the graph we're gonna look straight. Yeah, we're gonna look straight, and at certain point here, okay, at certain point here, it start to saturate. Okay, it start to saturate. So we call this region, yeah, saturation region. And then after from B to C, okay, from B to C, okay, the value of the collector current, okay, will increase slowly, gradually, yeah? slowly increase. That we call here is an active region, okay. And after more than, when the BCE becomes greater, okay, here we call a breakdown region, okay, breakdown region. And then you can see another graph here, okay, another graph here. When IB, okay, when IB, it means that when base is 0, the value of currents is 0, there will be a slightly, it means that the currents of the collector at the collector is not 0. Okay, because of why? Because there is a holes here, yeah, a holes current axis here. We call here is cut off region. Okay, so usually it is very slightly here, and it is very difficult to see. So we call here it is a cut off region. Yeah. So I think we're gonna look later. It is not enough time to finish all the slides today. We're gonna look later on. What are the characteristics for each bias? Okay, the reverse active bias, saturation bias. How to decide it is in a saturation part? How to decide the transistor in a forward active part or cut off part or a reverse active part? Okay, so I'm gonna explain later on tomorrow. Okay, much more detail about this. Yeah, and another. So we're gonna go for tomorrow, yeah. So from here, you have to remember also, yeah, the reverse forward, the BC and the BE junction condition. If it is in what condition, it will be what type of mode. So this also you need to memorize too. So I'm gonna go explain into detail tomorrow. So up until now, any questions? Oh, yeah. Any of you haven't taken note the attendance yet? Adakah yang boleh ambil attendance? I hope no, yeah. Alright, so if there is no question, our class now. Thank you very much. I hope you will do your revision for your test. Good luck for your test.
Thank you, Sensei.
Thank you. Arigato ne. Assalamualaikum. Good afternoon. Soalan susah ke tidak? Soalan I think the questions half-half lah. Yeah? Half-half. I think for paper 1 it's not too difficult, but be careful with the Zina lah. Okay? Be careful with the Zina. I didn't make your question for Zina part. So yeah, just go through the exercise that I gave to you. I hope you can do it. Okay, go through the exercise that I give to you. Right. Good luck. Okay. Assalamualaikum.